Welcome to Activity 7.2, Changing Directions. So right now you should be on page 86 of your book, but please understand that depending on what year you're listening to this video in, it could change, the page number could change. So it was a different number last year, it's a different number, could be a different number next year. So you should be on Activity 7.2, Changing Directions. So that's the important thing. This year it happens to be page 86. Our learning target is we're going to analyze the way a ball moves when being pushed or pulled from the side. So what we're going to do is focus on this question. What kind of forces will cause an object to change directions? And before we begin, I'd like to cover a little vocabulary here. What does speed mean and what does velocity mean? Do you know the difference between the two? Well, speed simply means how fast an object is moving, say 55 miles an hour, 5 meters per second. Velocity is similar to it, but it's not the same. Velocity actually includes the speed and the direction the object is moving. For example, 55 miles an hour north, 5 meters, sorry about that, 5 meters per second down, those are velocity. Now, one of the things we want to wrap up, if you remember this sheet, one of the things you filled out was, all these, but look, there's something new here. So go ahead and pull out the sheet from 7.1, add changing directions into your sheet. So if I go there and I cover that up, so I'll just pretend you didn't see it. What do you think, what causes things to change directions? If you're thinking unbalanced forces, you're correct. So you notice most of these are unbalanced forces, whether it's coming from behind something, pushing it forward, or whether it's slowing something down, all those are unbalanced forces. The only thing that were balanced forces are things that are motionless and on constant speed. So in order for something to change directions, you have to have unbalanced forces acting sideways. So that's what we're going to do, and that's what we're going to create today. So what I'm going to do first is I need you to pick up a softball for me. So your group may be all in the same spot. You're going to do this lab as a group. Maybe you're working by yourself. Just come grab a softball. What you're going to do is you're going to tap the softball while it's rolling. I want you to try and tap it 3 ways. First of all, tap it right from the side so it's perpendicularly to its original direction of motion. So roll it across your table. Again, not so fast. It says gently, so it shouldn't be landing on the floor. It shouldn't be hurting anybody. But if you roll it, tap it from the side so that your hand is hitting the tennis or the softball perpendicularly. Then what I'd like you to do, well, watch what happens, but then I'd like you to do it again. But now tap it so that it's slanted against its initial direction. So as the ball's rolling, you're going to tap it from the front side, not perfectly in front, but slanted from the front. What happens to it? Now try it one more time, and you're going to tap it slanted so that the tap both pushes the ball forward and to its side. So as the ball's rolling, you're not going to push it from its side, but you're going to push diagonally on the side and from behind it. So you're tapping it in the same direction that it's rolling. So do those 3 things, and what do you notice? What do you see? What do you observe? So go ahead, pause the video and do that. All right, now that you've had a chance to do the experiment, what I'd like you to do is answer A and B. Go ahead, pause the video. Did you pause the video, or are you just waiting for the answers to pop up? So I'm going to move ahead, and I'm assuming you already answered A and B. So let's talk about C. Repeat the former procedures using a ball bearing and a single magnet. Instead of tapping the ball bearing, just bring the magnet close to it from the side as it rolls. So what it's asking you to do is come up and grab some more supplies. One of those supplies is going to be a magnet. And what I want you to do is just kind of put your magnet on the table. And you can move the magnet as the ball bearing is rolling. But what I'd like you to do is take a ball bearing and just roll it. And as it's rolling, bring this magnet up close to it. And if it's too far away, it won't work. But as you get it and you adjust it so that it's close to it, what happens to the ball bearing? Does it go off to the side? Is it pushed away? Does it go straight? Try this several times. Try flipping the polarity of it and putting the north on one side and then putting the south on the other side. So go ahead and answer question C with the ball bearing. Does the ball change directions after passing near the magnets? Explain. So go ahead and pause the video and do this. So I hope you paused the video. So go ahead and repeat this procedure using two magnets, but put the magnets on different sides of the rolling ball or on the same side. So what it's asking you to do this time is to try the experiment again, except maybe this time you have two magnets and maybe you'll have a north here, maybe you'll have a south here. Try rolling the ball in between. What does it do? Try changing the polarities. Does it do anything? And then try it again. This time, maybe you put the two magnets right next to each other and you roll the ball by. Does it change the direction? Does it make it bend one way or the other way, more or less than when you only had one magnet? So go ahead and experiment with the magnets while you're doing D. All right, so the scientific principle that we've covered today is changing directions of motion is caused by unbalanced forces acting sideways. So just like a lot of the other things we've done, I'm not just telling you that this is the case. You actually, hopefully, you proved it true both with the softball and with the magnets today and the ball bearing. So make sure if you have any questions, you see me or ask questions. But what we're going to do now is we're actually going to go through the answers to see if you're correct. So does the ball always change directions? Yep. The ball will change directions if you apply a sideways force to it. Now, does the direction in which the ball was tapped, whether you did it from the side, whether you did it slanted, have any effect on the direction in which the ball changes? Absolutely. Now, I did put yes and no for a reason. If you have the ball and you tapped it from the side, it's going to change directions, but it's still going to go forward. So some people will say, well, no, it's still going forward. Yeah, it's still going forward, but it is going to go in a slightly different direction. It's not going to go straight forward anymore. It should go off to the side. So the best answer is yes, the force is slanted backwards or forward. It still pushes the ball to the side. It still makes it change directions. For 3, it should have. If you got the ball bearing close enough to the magnet, it will cause it to change directions. Why? Because it's applying a sideways force to it. And that should be the same here. The magnets have a greater effect if you put them both on the same side, or at least it should have, so it should have slanted more. However, an interesting thing, if you put it on opposite sides, they might actually counteract each other. And if you can get the ball bearing to go right through between the two magnets, you may not see any change in direction just because they counteracted each other and they canceled each other out. So if you have any questions about activity 7.2, make sure you have this complete. Just ask questions of your teacher. Thank you.